Now, this is known as number system, and I want to begin by saying that the way computers understand, as I began in the other class, or we have discussed over throughout this course, that computer understands only 1 and 0. That is the instructions that a computer can understand. For example, when you type in your keyboard, the way you are pressing 0, 1, 2, or 3 in your keyboard, that one is interpreted in terms of ones and zeros by your computer. That is why it is important for us to be able to appreciate number system, considering how computers take and understand instruction in form of 1 and zeros. Okay, as a definition, I want to agree with you that a value of a digit in a number, the value of a digit in a number is determined by 3 key things: the digit, the position in the number system, and the base of the number system. 3 key things that you need to get straight. Value of a digit in a number is determined by the digit, the position, and the base of the number system. So before beginning anything, you need to get the 3 aspects so that you can be able to see these positions varying. So I've said the value of each digit in a number is determined by the digit, the position, and the base. Now, in this number system, I want us to appreciate 3 types of numbers: the decimal number, the octal number, the hexadecimal number, and of course, the binary number. So I hope we have a clear understanding that we want to talk about the binary, the octal, hexadecimal, and decimal. I'll start from decimal. As soon as you enter the class, kindly mute so that you don't disturb the others. So I'll begin from decimal number. A decimal number is the normal natural numbers that we have in mathematics. And these are numbers which are ranging from 0 to 9. When you talk about any decimal number, is the normal numbers that we normally have in our real daily life situations, the computations that we normally have. In computer science or in computing, the way it is actually is that when I talk about a number like 5, for example, that number has actually base 10. Let me share you some whiteboard. I hope you can see that whiteboard. Eh? Okay, so I'm talking about decimal numbers, as we have agreed. We are talking about hexadecimal numbers. We're also talking about binary numbers. That's binary. And then we also talk about octal numbers. Now, as I begin, decimal numbers are known as base 10. Hexadecimal numbers are known as base 16. Binary numbers are base 2. Octal numbers, base 8. I want to explain this. I said the way you would interpret normal mathematics. For example, if I write 6 in decimal representation, it should be written like that. That is how 6 is known to be decimal number 6. Otherwise, it might be any other number. It could be even an octal number. It could be an hexadecimal number 6. So I was saying that the normal natural numbers in mathematics, or the normal numbers we do have in our real day life situations, are actually decimal numbers, and they are base 10. See, if someone tells you to write 8 in computer science, then you must write 8 like that. Then you put in 10 to communicate that this is actually decimal 8 or normal natural number, decimal 8. Now, yes, any question? I can mute this. Remember, you will be doing an assignment after this class. So it is very, very important to be very careful. Okay. So I was just showing you the decimal numbers. So when I say base 10, you understand that these are normal natural numbers and the way they are represented. Now, there are other numbers here, which you have seen, like binary numbers. Binary numbers are known as base 2. So as soon as you write any binary number, for example, if I would be writing a binary number, I would write like 1, 0, 1, 0, 1 like that. This is 20, 21, base 10. If I'm representing this, this is the decimal equivalent. This is a binary number. See? So this is a binary number, 10101 is equals to 21 base 10. This is decimal equivalent of that. So I was talking about the binary number is represented in form of ones and zeros, and it uses the number 0 and 1. Decimal numbers uses letters from 0 to 9. Hexadecimal number uses 0 to F. I'll tell you what is this F. And then the other one is octal number, which uses 0 to 7. Technically, if you count 0 and 1, it is actually 2. That's why it is known as base 2. When you count from 0 to 9, you get 10. That is why you would see decimal numbers represented as base 10. 0 to F, you count this one, it gives you 16. 0 to 7, this one gives you 8. Just wanted you to just get an overview of that before I proceed. Now I go back. So we were talking about this binary number. The most important thing you need to understand is how to be able to convert this. For example, starting from this binary number, you have been given binary number 10101, and this is number 21. How do you convert this binary number to its equivalent decimal number? And be very keen because we'll be doing straight away an assignment on this. So I want to convert binary number 10101 to normal decimal number. What I do, I multiply by increasing powers of 2, so that the first digit of this binary, 1, I multiply by 2 raised to 0. 0 multiplied by 2 raised to 1. 1 multiplied by 2 raised to 2, like that. That's why I'm saying increasing powers of 2. So that 2 raised to 0 times 1, 2 raised to 1 times 0, like that. So you can be seeing this binary number like that. So that I would want to convert binary number 10101 to decimal. I just multiply by increasing powers of 2. So hoping that you have now known how to convert a binary number to its relevant decimal number by multiplying by increasing powers of 2. If you have a question, it's good to ask immediately so that I know whether you have a challenge.
Okay, excuse me, sir.
Yes.
I have not understood on how to convert those numbers into decimal numbers. Can you pardon, please?
Yes, I want to repeat. I've said the way you convert is that you multiply by increasing powers of 2. so that, for example, I have 1, 0, 1, 0, 1. Remember, I said as a characteristic, I must have introduced and said binary numbers are numbers consisting of 1 and 0, and they're normally known as base 2. So you will be seeing something like that to signify this is a binary number. If it would have been a decimal number, you would write like this, and then you see this base 10. Now you are told to convert this binary number to this particular decimal number. So I said you multiply by increasing powers of 2, so that this one you multiply by 2 raised to 0. This 0 multiplied by 2 raised to 1, like that. This one multiplied by 2 raised to 2. This one multiplied by 2 raised to 3. This one multiplied by 2 raised to 4. And then you add all of them. You add. Once you add, you should be able to get 21. I hope that is okay. Don't ask the question.
Yes, sir. Yes, sir. Thank you.
Okay. So we can proceed. We proceed to octal number. So once you have understood binary number, you should be able to understand the other ones quite easily. So that octal numbers, as we have agreed, are numbers ranging from 0 to 7, and they are normally known as base 8. So you understand now what I mean by base 8. And remember, from the definition I emphasized that the value of a digit in a number is determined by the digit itself, the position, and the base. And you have seen binary is base 2, octal is base 8. As you have said, octal numbers uses digits 0 to 7, and they are also called base 8. So that you can see 12, 570 base 8. That tells you, as soon as you see 8 below as a subscript, it can tell you that this is an octal number. You are told again to convert this octal number to its equivalent decimal number. So what you do is, again, you multiply by increasing powers of 8, just the way you do it in binary numbers. So for this one, 12,570 base 8, I want to change this one to decimal. I just multiply this 0 by 8 raised to 0 times that, like that. So that 12,570, like that. This is base 8, and you are told this one should change to decimal. Remember, decimal now will be having an answer base 10. So 8, you multiply that by 80, multiply that by 81, 82, increasing powers of 8, like that. 83, 84. What you realize is that all these numbers, beginning from binary, moving to octal and hexadecimal, the 3 of them, if you want to change them to its decimal equivalent, you just multiply by its increasing powers of that base. For this one now, I'm talking about increasing powers of 8. And then you add, like that. So whatever you will get will be now its hexadecimal equivalent. So that we will be expecting 5496 base 10. I hope you can see these additions. Now, the other one is hexadecimal. You'll be given a number 19 FDE base 16. Convert this one to its decimal equivalent. Now, a number like this, 19 FDE. This one is base 16. Convert this one to its decimal equivalent. So you need to realize that this FDE I have not explained. Remember, I said these numbers, these hexadecimal numbers uses 0 to 9 and letters A to F. Remember, we have only one position to be occupied. For that reason, other than writing 10, 11, 12, 13, 14, 15, when you are 10, you represent 10 as A, 11 as B, 12 as C, 13 as D, 14 E, 15 F. So that if I count from 0 to 9 and A to F, I should be able to get 16. That is why it's actually known as base 16. So I hope you now understand how you are getting these alphabetical letters. So as soon as you see a number 19 FDE, F should be 15 at the back of your mind. D should be 13. E should be 14, like that. So I hope we are together on that. Now you are told to convert 19 FD base 16 to its decimal equivalent. So it should be 19 now, F, D, E. And I said you multiply by increasing powers of that particular base. So E will be 16, 0. D multiplied by 16, 1. F multiplied by 16, 2. 9 multiply, remember I said it uses numbers 0 to 9. So I would not want you to confuse and start saying 19. It is nothing like 19. It is actually using from 0 to 9. So F multiplied by 16, 2. 9 multiplied by 16, 3. And then 1 multiplied by 16, 4. Like that. So in the first line of your expansion, you will actually represent 16, 0 multiplied by E, like that. Then you put in brackets and then add 16, 1 into brackets multiplied by D. Adding like that. 16, this is 0, 1, 16 raised to 2 multiplied by F. Put in brackets again. Then 16, 3 multiplied by, like that. But as soon as you finish the expansion, you can come now and replace, knowing that E is, consider A, B, C, D, E, F. So that A is 10, this one is 11, 12, 13, 14, and then 15. So that E is now 14, D is 13, you replace, and then F is 15. So in your second line of expansion, this is your first line, you need to show and represent considering their individual letter representation, alphabetical letter representation. In the second line, you can now replace by the individual real numbers, knowing at the back of your mind that D is 13, E is 14, F is 15. Then you do it in your calculator. You should be able to get the decimal equivalent of this hexadecimal number 19 FDE base 16. Unless there is a question on that. I hope now you are comfortable to convert decimal, binary, octal, and even hexadecimal. The three numbers, that is binary, octal, and hexadecimal, to its relevant decimal equivalents. And I said decimal is the normal natural numbers. So you are now comfortable converting the three into its decimal equivalent. And I said, the only thing you do is, if it is binary, multiply by increasing powers of 2. If it is octo, multiply by increasing powers of 8. If it is hexadecimal, multiply by increasing powers of 16. Like that. Now, I move to the second section where I'm talking about shortcut methods and the others. So, for example, that's going the other way around. Whatever we have seen is converting octal, binary, and hexadecimal to its decimal equivalent. Let's see the other way around of now moving from decimal to binary. So, as you can see, I would want to illustrate with this one. You are told to convert a number such as 21 base 10. That tells you this is a decimal number, and they want a binary equivalent of this. So what you normally do is you divide by 2. So that 21 divided by 2 is 10, remainder 1. 10 divided by 2 is actually 5, remainder 0. 5 divided by 2 goes into 2, remainder 1. Then 2 divided by 2 is actually 1, remainder 0. Then 1 divided by 2 is not possible. 1 divided by 2 is not possible. Then it becomes 0, and that 1 remains as it is. Now, what you can see on these remainders, this particular remainders forms the binary number that we are interested in. So that the answer now will be 1, 0, 1, 0, 1 with a symbol there to signify this binary. Hope everyone is okay on that. Anyone who has a challenge on that? Before I proceed, no question. It means you're okay on that. So that's how you change 21 or binary number 21, or getting decimal number 21 to its binary equivalent. So knowing how to change decimal to binary. So you can see that you just divide by 2, and whatever remains as a remainder is what forms your binary number. I hope we are okay, because we'll be doing an assessment straight away on binary. So make sure you are very keen, actually very keen. So I hope we are okay on that. Anyone who has a question? Okay. If there's no question, I can proceed to something else. Okay, I stopped share. Now, as soon as you have seen that if I'm dividing, for example, here, you'll be given number 29 base 10. This is a decimal number. Again, you're told convert this to binary. And as we said, you divide by 2. Can you see here this scenario? 29 divided by 2 is 14. What remains? 1. 14 divided by 2 is actually 7. What remains? 0. 7 divided by 2, you get 3 remainder, 1. 3 divided by 2 is actually 1 remainder, 1. Then 1 divided by 2 is not possible. If it is not possible, you put 0 as the result. 1 divided by 2 is 0, because we don't need decimals here. So 1 divided by 2 is 0. What remains is 1, because that one has not been divided. So giving you 1, 0, 1, 1, 1 as number 29 in binary. Now, how do you write this? You write going upwards from the least to most significant digit. You see? So you can see as mentioned in step 2 and step 4, the remainders have to be arranged in a reverse order so that the first remainder becomes the least significant digit and the last remainder becomes the most significant digit. So you arrange going upwards so that you write your results as 11101 with a binary representation 2 below it. Please kindly mute if you have entered class. Please
Hello,
mute. Please mute. Raphael and the query. Please mute. Mute. Please, please. Yes. Anyone who was not muted, I can hear some background interference. Please make sure you have muted everyone. I don't want to go around checking who was unmuted or not, because I'll be wasting time. So make sure you've muted, otherwise I'll remove you out of my class. So I was talking about, who is this giving us disturbance? Gentle word. You know, I don't know what motivates someone to start unmuting in class. Jedida Mwende, kindly mute. So I was talking about converting from decimal to its binary equivalent. Yes, if you are entering the class, kindly be patient. If you have come late, be patient, unless you have a question. So I will proceed. Since you have known how to convert from decimal to binary, I want us to check other base system to decimal. For example, again, you're taking the other way around. Convert this binary 111101 to decimal equivalent. I'm repeating for purpose of those who entered the class late. So this is a binary number. Can you convert this one to a decimal number? We said you multiply by increasing powers of 2. So that you can now see here, we are multiplying 1 multiplied by 2 raised to 0, 0 multiplied by 2 raised to 1, 1 multiplied by 2 raised to 2, like that, increasing powers of 2, so that you can be able to change the binary number to its relevant decimal number. Hope that one is very clear now. Can you see here a scenario of octal number 25 base 8? To convert this one to its decimal equivalent, remember we said you just increase 8, multiply by increasing powers of 8. Any other conversion requesting you to convert to decimal, just multiply by the base, increasing powers of that base. So that's why we are saying 80 multiplied by 5, 80 multiplied by 2. It's multiplied by 1, that is 8081, like that. So that you can be able to get the decimal equivalent. That is why 8 raised to 0 is 1, 1 times 5 remains 5. 81 remains 8 multiplied by 2 to get you 16 plus 5. It gives you number 21 base 10 again. So get how to convert this to its decimal equivalent. Again, you're given a number 25 base 8. Of course, this is equals to 21. You have been given 21 base 10. Can you convert this to binary? That's what we did in our example. You just divide by 2. Then whatever remains forms the binary number 101010. So I have said once and again, remainders forms the binary number. So we have other methods like shortcut method. And for you to be able to use a shortcut method, it means that you must have tables. There is a table of octal numbers and table of hexadecimal numbers. So maybe I should discuss about that so that we move to shortcut method. So when I talk about a shortcut method, for example, remember I said for us to be able to use tables, you need to generate those tables for octal numbers and tables for hexadecimal numbers so that you can be using the shortcut methods. Now, in addition to what we introduced, hexadecimal numbers is a combination of 4 bits. Octal numbers is a combination of 3 bits. To start with, I'll just use octal numbers, and then you just generate the table of hexadecimal numbers as an assignment. So octal numbers begins from 0, 1, as we agreed, 2, 3, 4, 5, 6, 7. Now, 0 would now become 0, 0, 0. That is binary. Kindly mute, my friend. Please, as you enter class, mute. 1 becomes now 0, 0, 1. Can you see 1 in binary? 0, 0, 1. Octal number 1 in binary. Number 2 would be 0, 0, 1 plus 1. 1 plus 1 is 0 carry 1. 0 plus 1 becomes again 1. This becomes 0. So this one becomes 0, 1, 0. Again, add 1. 0 plus 1 is 1. Then you come in with that one, 0. So this one becomes 0, 1, 1. Now plus 1. So 1 plus 1 is 0 carry 1. So 1 plus 1 again, 0 carry 1. It becomes 1, 0, 0, 0. So 1, 0, 0. Again, add 1. If you add 1 here, it becomes 1, 0, 1. What I want to emphasize is 1 plus 1 is 0 carry 1 in binary. That's what you only need to understand to be able to generate these tables. 1 plus 1 is 0 carry 1, like that. So it becomes 1, 0, 1. Sorry. Should be this. One, 1, 0. Again, add 1, it should be now 1, 1, 1. Interesting to note that we have been able to fill all these spaces. You can see when we began, it was 0, 0, 0, 0. But at 7, we're now talking about 1, 1, 1, 1. You have filled all the spaces. Remember, at the introductory of this class, I said the value of a digit in a number is determined by 3 key things: the digit, the position, and the base in the number system. This is where the position plays, very important, that we have all been able to fill all the positions. 0, 0, 0 up to 1, 1, 1, 1, 1. Now, our interest was to be able to use this shortcut method to be able to do conversions. Now, you're given a number such as 2, 5, base 8. Remember, this is table of octal numbers. So I can use 2, 5, base 8. I want to change this one to binary. What is 2? 2 in binary is 0, 1, 0. What is 5 in binary? 5 in binary is 1, 0, 1. So I'll just come and bring it here, 1, 0, 1, naturally like that. What is this number? Any 0 in front of a number doesn't mean anything. So you can just drop this 0. Even if I place 0 in front of a number like that, or if I place 0 in front of 8, this 0 is insignificant. What makes sense is 0 from this other side. So I can just delete that 0. That number remains 1, 0, 1, 0, 1. And to know it is binary, you put it like that. So I hope you have seen how I've converted this number 25 to make this particular binary number. So you can say that 25 base 8 equals to 10101 in binary. You can as well change again this to decimal by multiplying by increasing powers of 2. You will get 21 base 10. So you can see the octal, the binary, and the decimal equivalent. But you can see how it is very easy when you are using the table of hexadecimal numbers. Most importantly, what you only need to know is hexadecimal numbers are using which binary. That is it. Which combination of binaries. For example, I said octal is a combination of 3 bits. As soon as you know that, you are through with the table, because you can only be adding 1, 1, 1, 1, 1 like that. And as long as you have in your mind that 1 plus 1 is 0 carry 1, then you are through. I hope you have seen how to use shortcut method, because you just place on, you just see how it is in the table. If it would be a table of hexadecimal, and I want you to do that. Remember, hexadecimal starts from 0 to, it is 0 to, from 0 to 9. Yes. I said it starts from 0 to 9 and letters A to F. So I want you to generate the table of these hexadecimal numbers so that you can be able to use shortcut method. So you will, at the back of your mind, you need to be understanding that you start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then A, B, C, D, E, F. All these ones form 16. So you start from here. I want you to do that as an assignment. Go straight away, you will get this assignment or a question asking you to use this. Now you can see I'm using combination of 4 bits as opposed to 3 bits. Again, 00001 plus 1. I'll just add this. Zero, 0, 0, 1 plus 1. So 1 plus 1 is 0 carry 1, bring 1, 0, 0, like that. So you can see this is 0, 0, 0, 1, 0. Again, add 1. The concept is just addition of 1. There's nothing else new. It becomes 0, 0, 1, 1. That is 0, 0, 1, 1. Again, add 1. Remember I said 1 plus 1 is 0 carry 1. Again, 1 plus 1 is 0 carry 1. 0 plus 1 is 1 and 0, like that. Binary addition is almost similar to arithmetic. The other ones we normally know arithmetic addition. So that 0 plus 1 is 1. But the only deviation is 1 plus 1 is 0 carry 1. So it becomes 0, 1, 0, 0. The other one becomes now 0, 1, 0, 1. Like that. You can figure out how you want to do this. If you want to follow a pattern, if you want to follow whichever formula you want, as long as you can be able to generate this table. There are many ways you can follow a pattern. So as you can do that up to where you end at 1, 1, 1, 1 at position F. So all the way from 0 to 9, A, B, C, D, E, up to F. I hope we are together, unless there's someone who doesn't understand what I'm trying to explain. Anyone who needs an explanation? Now I'll move to this. So once you have known, you can be able to compare like 10101. This is, remember we had just done a table of hexadecimal numbers. So you just compare with the table, straight away compare with the table, unless you have a question. You compare straight away with the table, hexadecimal compare with the table. For example, 1010, compare. Remember hexadecimal numbers uses combination of 4 bits. Octal numbers uses combination of 3 bits. So be cognizant on that. That's how you can use a shortcut method. Let's there's a question. Any question? Wangoi? Wairum? Yes? Okay, so that is it, unless there's a question on number system. Any question on number system, class?
Hello, sir.
Yes, yes, yes.
Okay, I was wondering when you
Yes.
said 0011 plus 1.
Let me have a writing board here. Then you can let me know. Stop sharing whiteboard. Now, yes, you're explaining what?
I was explaining about, okay, will you
Yes.
please write 0011?
0011. Yes.
So plus 1 it will be?
Or like this. If I add 1.
Yeah.
Like that.
Yes.
Now this one is 1 plus 1. It becomes 0 carry 1.
1.
Again, 1 plus 1, 0 carry 1. 0 plus 1 is 1. Then you drop that 0.
Okay.
Comes that number.
Thank you. Okay, thank you.
Is that clear?
Yeah.
Yes. So the key concept is knowing that 1 plus 1 is actually 0 carry 1.
Okay.
Yeah. As soon as you get the concept, 1 plus 1 is 0 carry 1. So 1 plus 1, 0 carry 1. 1 plus 1 again. 1 plus 1 again becomes 0. Sorry. 1 plus 1 is 0 carry 1. Then 0 plus 1 is 1. You can see this one is the normal way we do the arithmetics. That is 0 plus 1 becomes 1. Then you drop that 0. The only thing I've introduced is 1 plus 1 is 0 carry 1. Any other question?
Yes.
Yes. Anything that you need to be clarified?
Yes.
Yes. Come up, please.
Okay. The concept of converting the binary number
Yes.
into a decimal.
Yes.
Into a decimal.
Binary to
Was
decimal.
for-
Yes.
Yep.
Binary
Yep.
to decimal, like that.
Yes.
So I want to just explain this one very quickly. She's asking about converting from that is from binary to decimal. So we said that whether you are talking about binary, octal, or hexadecimal, all these three, converting them to decimal equivalent, you just multiply by powers of that particular base. For example, a binary number would be 1, 0, 1, 0, 1. This is a binary number. As long as you have seen something like that, that tells you there's a binary number. If you see something like this, 25, base 8. As long as you see base 8, this is an octal number. 19, F, D, like that, base 16. This is a hexadecimal number. Whichever circumstances, as long as you are changing these to decimal numbers, you multiply by increasing powers of that particular base. So for this one, you will say 1 multiplied by 2 raised to 0, 0 multiplied by 2 raised to 1, 1 multiplied by 2 raised to 2, 0 multiplied by 2 raised to 3, and then 1 multiplied by 2 raised to 4. Then you add all of them. Is that clear? Don't ask the question.
Yes.
So you are talking about binary to decimal. So whatever you want to do is just multiply by increasing powers of that base. Even if it is octal, you now multiply, for example, 5 times 8 raised to 0, and then again 2 multiplied by 8 raised to 1, and just add. Then it will be able to give you the decimal equivalent again. This one is 16 multiplied, 16 raised to 0 multiplied by D, 16 raised to 1 multiplied by F, 16 raised to 2 multiplied by 9, then 16 raised to 3. Increasing powers of that particular base should be able to give you the decimal equivalent of those individual numbers. Any other question? Yes, class. Any other question on number system? Yes, class.
I have a question.
Yes.
You have said that you add. How are you going to add?
Is you just add the normal way. For example, let me use this example. Now, you had this number 1, 0, 1, 0, 1. This is a binary number, and you want to get the decimal number. And I said multiply by increasing powers of 2 and add. So the first one is you start from and let's pick this areas again. So starting from 2 raised to 0 multiplied by 1, you put that one into bracket again. 2 raised to 2, 1 multiplied by 0. I hope you are seeing how the addition is coming in. Again, 2 raised to 2 multiplied by 1. 2 raised to 3 multiplied by 0. It's multiplied by 0. Then the last one is 2 raised to 4 multiplied by 1. Then you add all of them. So that 2 raised to 0, any number raised to 0 is equals to 1. So 1 times 1 becomes 1. This one is times 0. Anything times 0, it goes like that. So this one goes away. And then this one also goes away because it's multiplied by 0. So you are remaining with 2 raised to 0 times 1. Any number raised to 0 is 1. So remains 1. 2 raised to 2 is 4. So this one is 1. The other one is 4. 2 raised to 4 is 16. So 16 plus 4 plus 1. What do you get? 21. Base 10. So I hope you have seen how we have come in to convert that binary number to decimal number. You see now addition comes in. Is someone asking?
Yeah.
Okay.
Yeah.
That's clear. So any other question? Any question? Any other concern? Okay, if there's no question, I would agree with you that you now understand the number